Chapter 1.2 Cluster Architecture. A Kubernetes cluster is composed of a control plane and worker nodes that run containerized applications. Each cluster requires at least one worker node to run pods, which host the components of the application workload. The control plane oversees the worker nodes and pods, with multiple nodes in a cluster for fault tolerance and high availability. The document outlines the necessary components for a functioning Kubernetes cluster, with flexibility in the distribution based on specific setups and requirements. Control plane components. The control plane in a Kubernetes cluster is responsible for global decisions and event responses. Components such as Kube API Server, etcd, Kube Scheduler, Kube Controller Manager, and Cloud Controller Manager play crucial roles in managing the cluster. The Kube API Server is the front end of the Kubernetes control plane and can scale horizontally by deploying multiple instances. etcd is a key value store used as the backing store for cluster data, and it is essential to have a backup plan for its data. The Kube Scheduler selects nodes for newly created pods based on various factors like resource requirements, constraints, affinity, and anti-affinity specifications. The Kube Controller Manager runs controller processes, which handle tasks like monitoring node status, managing one-off tasks, and linking services to pods. The Cloud Controller Manager is a component that embeds cloud-specific control logic, allowing the cluster to interact with the cloud provider's API. It separates components that interact with the cloud platform from those that only interact with the cluster. This component is not necessary for on-premises or learning environments. Like the Kube Controller Manager, the Cloud Controller Manager combines multiple control loops into a single process that can be scaled horizontally for performance improvements and failure tolerance. Controllers that may have cloud provider dependencies include the Node Controller, Route Controller, and Service Controller. Overall, the control plane components in a Kubernetes cluster play essential roles in managing and maintaining the cluster's operations efficiently. Node components. Node components such as Kubelet and kubeproxy are essential for maintaining running pods and providing the Kubernetes runtime environment on each node in a cluster. The kubelet ensures that containers are running in a pod by taking pod specs and ensuring the containers described in them are healthy. The kubelet does not manage containers created outside of Kubernetes. On the other hand, kubeproxy is a network proxy that implements part of the Kubernetes service concept, maintaining network rules on nodes to allow network communication to pods from both inside and outside the cluster. Container runtime is another crucial component that manages the execution and lifecycle of containers within Kubernetes, supporting runtimes such as Containerd, CRI-O, and any other implementation of the Kubernetes CRI. Add-ons in Kubernetes use Kubernetes resources such as Daemonset and deployment to implement cluster-level features. These add-ons are typically placed within the kube system namespace. Some essential add-ons include Cluster DNS, which provides DNS records for Kubernetes services and is necessary for many examples. The Dashboard add-on is a web-based UI for managing and troubleshooting applications and the cluster itself. Container Resource Monitoring records metrics about containers and provides a UI for browsing the data. Cluster-level logging saves container logs to a central store with a search interface. Network plugins implement the Container Network interface and allocate IP addresses to pods for communication within the cluster. Architecture variations. The text discusses the various deployment options for the control plane components of Kubernetes, including traditional deployment, static pods, self-hosted deployment, and managed Kubernetes services. It also touches on workload placement considerations, cluster management tools like kubeatom, kops, and kubespray, and customization and extensibility options within Kubernetes architecture. Understanding the different deployment options and variations in Kubernetes is crucial for designing and maintaining clusters that meet specific operational needs. These options allow organizations to tailor their clusters to specific requirements, balancing factors such as operational complexity, performance, and management overhead. The placement of workloads, including control plane components, can vary based on cluster size, performance requirements, and operational policies. Various tools and methods are available for deploying and managing Kubernetes clusters, offering different approaches to component layout and management. The flexibility and extensibility of Kubernetes architecture enable organizations to customize their clusters with options for custom schedulers, API server extensions, and integration with cloud providers.